Yo, what is up guys? So today I want to showcase how you can implement your own stack data structure in C. So just to clarify some things, there are many different methods that you can implement in your own stack, but we're going to mainly focus on these basic methods here. We're going to initialize our stack, free our stack, we're going to push objects to the end of the stack, we're going to pop elements from the end of the stack, and return the object we've popped. We're going to be able to see what's the element at the top of the stack without having to remove the element using peek. We're going to clear all elements from the stack, and we're going to print the stack in such a way that we can visualize what's going on. So it's going to be very focused on teaching how you can understand how a stack works and how you can implement a stack in C. So there are mainly two ways you can implement a stack. You can use an array or you can use a linked list. So an array is basically a contiguous piece of memory that you can access a random index just by having the pointer to the first element, and then you add the offset, meaning n, meaning the index, or I'll call it I. I is the index times the size of the element that the array is storing. So if it's an integer array, you can just access the ith element just by having the address of the first plus I times size of int. Oh, and then you can access elements very easily. And it's pretty good to implement a stack using an array. It's a good idea because you are only concerned with the last element of the array always. And the only problem with using an array to implement a stack is that you would have to use a dynamic array, because once you have your fixed size array full, you cannot add more elements. So you would have to copy this array to a new array that is bigger, usually double the size of your original array, and then you can insert things there. But today I want to showcase how you can implement it using a linked list. So a linked list it looks like an array from the from the viewer perspective, but it works quite differently. So the way a linked list works is you, instead of just storing the value, so the value is this, instead of just storing the value, you also store a pointer. So this is the value, and this is the pointer to the next value. So these are blocks. We can call it nodes of the linked list. So there's a linked list and one, and then you have the value and the pointer, and etc. So it's really easy to insert elements in between elements in a linked list, because in an array you would have to shift all the elements after you've removed one element within the middle of the array. But with linked list, you just create a new element, point the old to the new, and then point the new to the other one, and that's how you can insert elements within the linked list. But as we're only concerned with the last element, we will have to loop through every single element in the linked list until we find an element that points to null, meaning that it points to nothing, right? There's no more elements. This is the last element. And then we're going to insert a new element here. We're going to create a new block, put this pointer to the new block, and the new block will point to null. And this will be the last element, right? The downside of implementing a stack with a linked list is that you have to run through the whole linked list until you find the last element. And that's why using an array usually benefits you from inserting in big stacks, because you can just index the last element and just add plus the size of the type you're storing in that stack, and you can access that index and store the value there. But I'm going to showcase how you can do that with linked list. So let's go. So our linked list will basically have a head. So the first element, once we start the linked list, this will be the head, and the value of the head will be equal to the number of elements within our linked list, meaning that we have n elements within our stack, and the pointer will point to the first element. When it's empty, we'll point to null. Once we add an element, we'll point to the next element. Okay, so imagine here, and this will be +1 because we've added an element, and now we have one element instead of 0 elements. Okay, and etc. So that's how we're gonna implement it, and let's go right into the implementation here. So we're gonna include some libraries and C here just to make our lives a lot easier. cd.io.h and include stdlib.h. So this is essentially for printing, and this is essentially for malloc. So we're going to allocate memory. So we're going to create our main function here. Basic return 0 if everything goes okay, and then we're going to create our stack pointer to our stack, and this will be pointing to null first because we haven't initialized it yet. And then the first function we're going to create is the stack function, right? And we're passing by reference our stack, so we can initialize the stack. So let's first create a stack. So type def struct node, and then we're going to create. So as we said before, our stack will be composed of different nodes that point to different nodes. So it's basically a linked list. So that's why we're going to create a node struct, and we're going to call it stack because this will represent our stack. So and we within this node we have a value. So that's the first element. So it will be a stack of integers. So that's why I'm creating the value as int. And so we have integer values, and we have a pointer to the next node. So struct node next. So we have a pointer to the next node. So this is essentially what we're doing here. We've created our struct. Now we have to create our init stack function. So first things first, it will be a void function. That's why we're passing the memory address of the stack, or the memory address of our pointer to the stack, because we can use a void function instead of returning the stack from the function. So init stack will be a pointer to a pointer. And what we're going to do here is use this trick here, that we're going to get a new variable for our pointer to our stack, just to make things a little bit easier. So this is a pointer to a pointer, and just we're dereferencing this pointer to be the pointer to our stack, and that's why we're getting the stack here. This is easier to read, easier to understand. So that's what we're doing here. So now that we have our stack within the function, we can modify the stack. First things we have to do is check if the stack is different from null, meaning that if the stack is different from null, it's already initialized. So we would tell the user that this stack has already been initialized. So that's why we check if it's different from null. And if it's not different from null, we will return it because it's already been initialized. If it's not, meaning that it's null, meaning that it hasn't been initialized, we're going to initialize it. To do that, we're going to create a temporary variable that will help us here. This will be essentially the variable that will create our node. We're going to allocate our first node using malloc size of stack. So we're basically allocating our first node, and we also have to check if our malloc was successful. So if temp is equal to null, meaning that our malloc was not successful, what we're going to do is we're going to tell the user that malloc returned null in initializing stack, meaning that we couldn't initialize the stack properly. So we're going to return it. For some reason, if the malloc fails, we have that catch. And if everything went right, we can now use our initialized memory address to store the value of the head. So this is the head. First, it has 0 elements. That's why the value is 0. And then the next element is pointing to null because we have 0 elements and we only have the head. So the head is pointing to null. And last but not least, we just point our stack, our original stack, back to temp, meaning that this was a temporary variable we've allocated, and now we change our pointer from null to the our first allocated head. So that's what we're doing here. And now what I want to do is I want to check how the stack is doing. So to do that, we can use our print function. So let's create a void print stack. And as in print stack, we're only going to print the stack. We're only going to read from the stack. We're not going to write anything from the stack. We can just simply use a regular stack pointer. So we don't have to pass the memory address of our pointer. We just pass our pointer. And from here, what we want to do is we want to read and check if first thing first, I want to check if the stack has already been initialized. So in this case, if the stack is null, meaning that it has not been initialized, we're going to tell the user that stack has not been initialized. Okay. So if the stack has not been initialized, we're going to return. And on top of that, I think that's all we need for now. We're going to check if the stack has not been initialized, and we also going to return if the stack is empty. So if stack value equals 0. So what we're essentially checking here is if the value of our head is 0, meaning that our stack has it is initialized but has no elements. So this is essentially empty. So this stack is empty. So the stack is empty, and return it. If the stack has been initialized and it has elements, we have to loop through all elements and print it. So stack while stack next is different from null, meaning that while we haven't reached the last element, I want to print it in the following format. So the element and a pointer to the next element, and we're going to print the stack value, or meaning our current value, and we're going to say that our stack equals our stack plus our stack next. So we're essentially looping through all elements until we reach the last, and once we reach the last element, I want to print the last element by itself and with a breakline. And we're going to print the value of the last element. Okay, so that's what we're essentially doing. And now what I want to do is test these functions. So let's just declare them here, the function declarations here, and this function as well. Let's paste it in here. Let's fix it real quick. And I want to check what the print stack function will return once we pass an uninitialized stack. So once we pass an uninitialized stack to the print function, it has to print that the stack has not been initialized, and we're going to print the stack right after we have initialized the stack, but it's empty. So it has to print the stack is empty. So we have to check it out first. So let's compile it. I guess everything is right. So GCC stack, no errors. So the stack has not been initialized. Okay, so the print function print the element, the stack has not been initialized, and we had an error here. It didn't print the stack is empty. So let me check what happened here. Oh, there it is. That's why. So I had a single equal here instead of double equals. So let's just recompile it and run it. So now everything works as expected. So when we print the stack on an uninitialized stack, it tells that the stack has not been initialized. And when we print the stack after initializing it with 0 elements, it tells us the stack is empty. So now let's insert some elements within the stack. So let's push some elements in the stack. And for that, we're going to create a push function that will pass in the stack. And we'll also pass the element we want to push. So as I want to push 0, 1, 2, 3, etc. And I want to check how the stack is being transformed accordingly every time we print an element. So every time we push an element, okay? So we're going to insert 0, and then we're going to insert 1, and then we're going to insert 2, and print to see how this will be working. So let's create a function here, push. Well, we'll receive a pointer to the stack, pointer to a pointer, and a value that we want to push. And we're going to reuse a lot of code here. So first, I want to check if the stack has been initialized. And I also want to allocate a new value here. And I also want to use the syntax here real quick, just to make things a little bit easier to read. So we're essentially using this, dereferencing the pointer to have our stack for visibility. And we're checking if the stack is null, meaning that has not been initialized, because we cannot push into something that has not been initialized, and then we return. If it has been initialized, we're going to create a new node, and the value of the node will be value. So we're inserting the new value. And as we're inserting at the end, the next of this node will be null, meaning that this is the last element. And from here, we just have to loop everything again, because we want to insert at the end, so we have to be at the end. So I'm going to copy this. I'm going to paste in here. So we're going to loop through the whole stack. We don't have to print. Oopsie. We don't have to print. We just have to reach the end. And once we reach the end, meaning that our stack element is representing our last element, we're going to say that instead of our stack representing our last element, the next element will be the last, and this will be temp. So this is essentially it. And once we have added this element before, we can either do this here, so stack value plus plus. So while the stack is pointing to the head, we can increase the head from 0 to 1 because we're going to insert a new value. Or we could do at the end here, but we have to use the reference to p and then this value plus plus. So either of these would work. I'm going to go with this one because I just want to increment the value of the head when I reach the end, not before it, okay? So now we're able to insert elements. And now if we print it, if we check it, the print function, it also prints the head. So when we have 0 elements, it prints the stack is empty. But once we insert number 0, it will print the head that has 1 element. So we print 1 and pointing to 0. And when we add 1, it will be 2 pointing to 1, pointing to 2, pointing to 0, pointing to 1. And when we push number 2, it will be 3 pointing to 0, pointing to 1, pointing to 2, meaning that we have 3 elements. So let's compile it. Oh, I just forgot to do the function declaration here. Let's just fix it real quick. Let's recompile it and run it. So this is essentially what's happening here. So I forgot to, the stack is empty. Where is it? The stack is empty. I forgot to add a break line here so we can visualize things better. So there we go. So first we create a pointer to a stack that is null. And when we print it, it says that the stack has not been initialized. Then we initialize the stack and we print it telling us the stack has been initialized but it's empty. And once we push elements, we're going to print the number of elements and the elements in sequence. So we have 1 element that is 0, and then we have 2 elements, 0 and 1, and then we have 3 elements, 0, 1, and 2. Okay? So now we want to have the ability to remove the element from the stack. So this is the pop function. So let's add here this pointer to the pointer stack, and we don't have to pass any value because we just have to remove the last element. We're going to reuse the same logic here. So check if the stack has been initialized. So let's get it. And also, we're going to loop to the end of the stack. And let's print it here. And once we reach the end, meaning that, let's now implement the logic to remove the element. So we're checking if the stack has been initialized, and we're going to loop through all the elements until we reach the end. Once we reach the end, I want to remove the last element. But before that, if we reach the last element, we cannot have the reference to the previous element. So we have to change the pointer from the previous element to null. So what we essentially have to do here to remove element is we have our stack and blah blah blah, and then we have the this is the last element. So this is the last element we want to remove. And before we remove it, we want to make the pointer from the guy that's pointing to here to point to null, and then we're going to free this memory. Okay. So instead of us going to the last element, we're going to loop until we find the second to last element, and then we're going to free the last and point the second to last element to null. So instead of our last element, we're looping to the last element. We're gonna loop until the next of next is different from null. Of next is different from null. So in this case, we're checking if the next of next is null. So the next element will be the last one, but we can only do that if the next we have a next to next element, right? Because if we do next to next in this guy, we're trying to access next to null. This doesn't make sense. So it has the list needs to have at least 2 elements. So next to next. So we're gonna check if the stack value is at least if it is 0, printf the stack is empty. We cannot remove elements from an empty stack. And now if we have 2 elements, at least 2 elements, the head. So let me get here. If we have at least the head pointing to the first element, in this case, the next to next element is null. So this will work, and then we're going to remove this guy and only remain with the head, right? So now what we have to do is we loop until the next to next is different from null. And once we reach that, we're going to say that a temporary variable that will help us, a pointer, will point to the stack next. And our stack next will be pointing to null. And then we're going to free our temp variable. And on top of that, we have to remove the value. We've got to lower the value because we removed an element. So what we're essentially doing is we're looping until we reach the second to last element. If it is the head in this example, our head is the second to last element. So the next element of the next element is null. Once we reach that, we're saving the stack next into our temporary variable. So we're essentially pointing a temporary variable to this guy. We're setting this guy to point to null. So this will point to null. And we're freeing this memory, and we're reducing the size or the value of the head from, for example, if we had 3 elements and we removed, now it's 2 elements. That's why we have to do that. So we have the pop function. Now we just have to test it out a little bit. So number 10, paste it. And let's attempt to use it here real quick. So we have to pop the stack, and we're gonna pop in print. So pop in print, Shift V, Y, pop. So we have 3 elements, 0, 1, 2. So we're popping 2, we're popping 1, then we're popping 0. And if we try to pop something that is out of the stack, we're gonna have to print that we're trying to pop from the empty stack. So it won't print, it won't pop. It will just say that the stack is empty. So let's recompile this stack and see if this what we would expect. Let me just add a print here. So printf. Oh, wait, what happened here? Okay. So printf, just to visualize things a little bit better. This is inserting elements, push. And here will be popping elements. So we're inserting and popping. Stack. So when we insert elements, we insert 0 and 1, and then we insert 0, 1, and 2. So we have 3 elements, 0, 1, and 2. And when we start popping, we pop number 2. So now we have 2 elements, 0 and 1. Once we pop 1, we have only the 0. So now it's 1 element and 0. And once we try to pop the stack from an empty, so now we have popped the 0. It says that the stack is empty now. Once we try to pop again, and once we try to print it, it says that the stack is empty. So everything is working as intended. Now the only thing we have to implement now are the functions to oh, this function also has to return, right, the element we've popped. So instead of being a void, it has to be an integer, right? Because the pop method, if you take a look here, the pop removes and returns the object at the top of the stack. So we also have to return an integer here. So let's return the value we want to pop here. So temp. Before we free temp, we're gonna say that last int last element, or top element. I'm gonna say top element will be equal to temp value, and we're gonna return the top element, right? And here we can just either return to nothing as we're doing here, or we could simply get the element we've popped. So let's get from this zero. Let's get here from the 0th element. So this is the great int last element equals the pop, and here we have to adjust it to return an integer. And now let's printf the last element, popped element. And now let's print the last element. Oh, so let's edit here, pop after pop and after pop, and let's get last element as well. Vword. Let's copy this, paste. Wait, what? There you go. Now we can check these elements and shift V, Y, pop, pop. Can delete this pop and this one. And I guess we're good. So now we can visualize that our pop function is returning the element. Return with no value in function, returning on void. Okay, so let's return 0 in this case. I just forgot to change it to 0 because, or once we return 0 here, sorry, this is the push function. This is the pop function. Okay, so now we can check it properly. So we insert elements 0, so we have 1 element, 2 elements 0 and 1, 3 elements 0, 1, 2, 3. When we start popping elements, we pop number 2, and then we only have 2 elements now, 0 and 1. Once we pop 1, we only have 1 element now, the number 0. And once we pop 0, the stack is empty. And once we try to print the empty stack, it says the stack is empty. So everything is working as we intended, as we expected. And now we're done with the init stack is okay, the push to the stack is okay, the pop to the stack is okay, and the print stack is also fine. We can also peek. So let's implement the peek here real quick, because the peek is basically a pop, but the only difference is that we'll not pop the element. We'll not delete the element. So let's copy this whole function here and basically paste it, and we're gonna call it peek, and we're gonna pass the stack, only the stack here. We're not gonna need this because we're not gonna change anything. If the stack is equal to null, hasn't been initialized, we'll return 0. If the value is 0, the stack is empty, so there's no element to be picked at. And then we're gonna return, wait a second, let me delete this. We're not gonna use this. So once we need to reach the last element in this case, so it's not next, so it's just next equal to null. And then we're gonna return the value of the last element. So this will be the stack value. So we're gonna loop through the whole stack until we find the last element, and we're gonna return the last element. And we can peek here in between every time we try to after we insert an element, we can peek. So after print stack, we're gonna peek. So let's peek before here. Peek. So every time we peek element, so it will be the same thing as pop. So we do peek at the top and pop at the bottom, right? Because they will do the same thing. So the only difference is that the peek will not pop the element. So let's run it again. So after we start inserting, we insert 0, so the peak element is 0. That's why we have one element 0. And then we insert 1, and the peak element is 1 because the last element is 1. And once we insert 2, the peak element is 2 because we have 3 elements, 0, 1, 2, and the 2 is the last element. And then we start popping elements. So we pop 2, we are left with 2 elements, 0 and 1. And we pop 1, we're left with 1 element, 0. And we pop 0, we're left with an empty stack. So everything is working as intended. Now we have to implement a clear function. So the peak function is pretty easy to implement, and the clear function will also be easy to implement. So let's just add here a new function, and this will be a void function because it doesn't do anything. This will be called clear, and the clear will be exactly the same thing as the pop, but it will not return anything, and we don't have to. Okay, let's just paste it in here. Let's delete this. So the idea is pretty similar. So instead of being pop, this will be clear. So we clear the stack. We do the checks as usual. And what we want to do is, the logic is a little bit different. So I want to delete every next element from the head. So I'll be looping through each element here. So the way it works is, let me just draw here to make it easier to understand the clear method. So we have the head pointing to another element and pointing to another element and then pointing to another one. So I'm going to keep the head, and I'm going to put the head to the next, pointing to the next element. This will not be here, and I'm going to free this element. And then I'm going to do the same thing. The head will point to the next element. This is not here anymore, and I'm going to free this element. And then we're going to point the next element to this, and then this is not here anymore, and I'm going to free this element. This will be null. So this is how we're going to free. We're going to loop, deleting every element in front of the head element. So while stack next is different from null, what we're going to do is I'm going to say that a temporary variable, so let's get it here, a temporary variable will point to the stack next, and the stack next will be pointing to the temporary next, right? And then we're going to free the temporary variable, right? And this works. This is all we need to do. And of course, we have to every time we free an element, the stack value has to decrease because we're removing elements, right? So that's what we're doing. So the pop, remove elements. Here as well, we're going to remove elements. So what we're essentially doing is starting the stack at the head like this. We're saying that the stack starts pointing to the first element, and while the next element of the stack is not null, meaning that we have elements in the stack, we're going to create a temporary variable that points to the next from the stack, so pointing to the first element. And we're going to say that our next from the head will be pointing to the next from the head. So we're doing this movement, and we're going to free this element and remove one from the value from the head because we remove this element. And we're going to do this until we reach the stack pointing to null. That is exactly what we're doing here. And we can check it out by re-adding some elements here. So I'm going to copy this. So I'm going to push elements, copy. I'm going to reintroduce more elements. I'm going to push elements. I'm not going to use peak. I'm going to keep the same structure. Doesn't matter. So, but I will not create this peak element again. And I will push, in this case, I will push like 5, 55, 89, and yeah, that's it. And then I'm going to clear. So I'm going to print f, clearing the stack. And then I'm going to call the clear function on the stack, and then we're going to print the stack after we clear the stack. Print stack, stack, and of course, after we clear the stack and we print the stack will be empty, so it has to print empty. So that is essentially what we're doing here. And let me just create a function declaration here: void clear stack double pointer, and that's it. So it's void, right? That's why it doesn't return anything. I guess we're good. So we can recompile it and run it. Clear stack return 0. Where is it? Oh, it returns nothing, right? Because it's a void. Let's recompile it and run it. So as expected, let me check here something real quick. Inserting elements push, and then we're popping elements, and then we print the stack. The stack is empty. And then we have to insert elements back again. Pop element 0, the stack is empty. Okay, let me just comment this out. Let's recompile it and run it. The stack is empty. Let me check if I'm doing something wrong real quick. Once we pop, and the stack is empty on the print. This stack is empty. This stack is empty. So when we pop here, this stack is empty. So popped element, last element. Okay, so we're not returning last element here, right? When we pop, this stack is empty, and then we return, right? We return 0. So that was my mistake. That was my bad. So if the stack is empty, we have to return -1. So let's say we return -1 here. Returns -1 if stack is null or empty. Okay, just leave a comment here. So now I think it's gonna work. Let's just recompile it and run it. So yeah, that is the expected behavior. So we just had to return it. So now if we recompile and run it, now we are doing the same thing we were doing before. So we're gonna insert elements, and then we're gonna pop elements, and then we're gonna reinsert elements. So we're reinserting elements here, inserting elements. We've pushed, so we peak at 5 because we inserted 5. And now we have one element, this is number 5. We have two elements, 2, 5, and 55. And then we insert 89, so we have 3 elements, 5, 55, and 89. So when we clear the stack and we print the stack is empty, right? So this is the expected behavior. And now the last function we need to implement is, where is it? This is the clear function. This is okay. And the last function we have to implement is the free stack, because we're freeing every single object once we clear the stack. But we have to essentially clear the head as well. We have to free the head, right? So to do that, I want to create the new function called free stack. That will be the exact same thing as this function. So let me copy. Let me paste it. What? It didn't copy for some reason. So let me copy this. Let me paste this. And let me insert this right here. And we're going to pass in the stack that we want to free, a pointer. And we're essentially going to free everything. And once we reach the end, we're going to say that our stack points, we're going to say that our temp variable that we're going to create, so our temp variable will be equals to our stack, because we're going to free this variable. Or we can simply free stack. Let's free stack. And once we free stack, we have to make that p is pointing to null, right? So this will point to null, and this will be freeing our stack, right? So I think that's essentially it. And we have everything ready to implement our last function. So this is the free stack function, and yeah, that's it. So let's copy this. Let's add to the function declaration. And at the end here, we can free our stack. Let's free stack. And let's print here that we're freeing our stack. Freeing stack. Let me add double break lines here to make easier every time we do this. It's a little bit easier to read. So we're gonna free the stack, and we're gonna pass in the stack. And once we free the stack, we have to print the stack just to make sure that this is freed up and it's null. So if it's null, it's gonna print to the console our, where is it? It's gonna print this stack has not been initialized. So let's just clear the screen. Let's recompile it and run it, and there you have it. So let's just revise it. And so first things first, what we're doing is we're trying to print a stack that has not been initialized. Once we initialize and print it, it says that the stack is empty. And then we start inserting elements. So we insert element and peak. So insert 0 and peak, that's why we receive 0. Now we have one element, that is 0. We insert 1 and peak, that's why we have 1 here, because it's the last element. And then we have 2 elements, 0 and 1. The same thing for 2, 3 elements, 0, 1, and 2. And then we start popping elements. So once we pop 2, we say that the element we've popped is number 2. and now we have only two elements, 0 and 1. Then we pop again, number 1, and now only one element, number 0. Then we pop 0, and the stack is empty. And then we try to pop again. The popped element is -1 because there's no element to be popped. That's why we return -1. So when we print it, the stack is empty because there are no more elements to pop. So we start reinserting elements into the stack. So we insert number 5. So that's why we have one element, number 5. And then we insert 55. That's why we have 2, 5, and 55. And we insert 89. Now we have 3 elements, 5, 55, and 89. And then we clear the stack, meaning that we're going to delete every single element within the stack. And then we print it after we clear the stack. It says that the stack, the stack is empty. So that's why it's saying here the stack is empty, because we've cleared every element, we've deleted every element within the stack. And when we free the stack, we basically, if there are elements in the stack, we're going to clear, and then we're going to free the pointer to our stack. That's why we're freeing the stack. And once we try to print the stack, it says that the stack has not been initialized, because we're essentially, where is it? The stack has not been initialized. So wait, this is wrong, because free stack, the stack is empty. We have to return here, okay? And here, we don't have to return if value equals 0. So if that is next equals null, the stack is empty. Okay, now we're good. Now we're good. That was incorrect. So let me just recompile it and run. Now we're good. So once we clear the stack is empty. If you have any elements when we free the stack, we're going to delete every single element. And once we reach the end, after freeing stack, it will print that the stack has not been initialized because we deleted every element, including the head, because we freed the head. And now our stack pointer is pointing to null, right? And that's it. That's how you implement a simple stack using C language. We're using pointers here. Hopefully this wasn't too confusing, and you kind of understood how the stack has been implemented, how the data structure is moving here. Of course, this is not the most optimal way to implement a stack, and there are many different ways you can implement it in C, but this is one way you can do it. You could create an API to make things easier so that the user doesn't have to initialize the stack and stuff, but this is just a simple way to implement a stack and to use it in your applications if you ever need a stack. Okay, so thanks for watching. In the future, I'll be bringing more videos about how to create simple data structures or more advanced data structures using C language or other languages. And that's it. See ya.